Welcome to this second session organized by session of the webinars organized by FFplus project. So we will focus on the impact provided by using HPC to first SME users, first HPC SME users. This will highlight the real-world success achieved by these companies during the sub-projects they realized. So just a rapid reminder of FFplus. FFplus is the successor of the Fortissimo series of programs. It's a European initiative dedicated to boosting the competitiveness of SMEs and startups by accelerating the adoption of HPC and AI. The project facilitates access to supercomputing resources, empowering businesses to solve complex challenges through advanced modeling, data analytics, and generative AI. So during the next 2 hours, we will demonstrate through success stories how high-performance computing can provide SMEs with significant competitive advantage. So we have planned 4 presentations. Let's go to the first presentation, which is dealing with HPC enhanced genomic selection for climate resilient crop breeding. So this will be made by Melina Niku. Melina is a climate change expert and meteorology PhD candidate at the Aristotle University of Thessaloniki. Her research utilizes crop and climate models to assess climate impacts on agriculture production, specifically wheat yields. With a background in rural and surveying engineering, her expertise spans climate modeling, geospatial analysis, and machine learning. As a research assistant and consultant, Melina translates complex environmental data into practical science-based adaptation strategies, contributing to projects focused on climate resilience, smart farming, and sustainable agriculture.
Hello everyone, my name is Melina, as Samir already introduced me. So the main idea behind Genesis is to use AI and genomic selection and high performance computing to help breeding programs identify promising crop varieties faster, and especially under climate change pressures. The consortium was implemented by 2 partners, by Bespoke, that was the technical partner, and by Bios Agrosystems, that was the end user and validation partner. So the problem is presented here from 2 perspectives, from the breeder side and the technology provider side. For breeding programs, the main challenge is that developing a new crop variety is still a very long and excessive process. It can take more than 10 years because varieties need to be tested repeatedly across seasons, locations, and environmental conditions. The results are also very local. A variety may perform well in one trial site, but differently in another, and that's because the performance depends strongly on microclimate, on soil, weather, and stress conditions. And this creates high cost and high risk. Field trials require land, labor, agronomists, measurements, and multiple years of validation, while climate variability adds uncertainty. Another challenge is that the conventional breeding struggles to evaluate several stress factors at the same time, such as drought, heat, and pests. And from Bespoke's perspective, the challenge is to take AI and machine learning methods that are computationally heavy and turn them into a reliable, repeatable, and scalable workflow that can actually be used by breeders. So, Genesis addresses both sides, faster and more scalable selection for breeders, and an HPC-enabled digital workflow that can become an operational service. Building on the business problem we just outlined for breeders and for us, as the technology provider, the key requirement is a workflow that can deliver reliable selection outputs fast enough to fit real breeding timelines, and at a scale that field trials alone cannot support. Genesis is our response to that need. An HPC-powered genomic selection pipeline that integrates breeding, genomic, and environmental data in a single repeatable process. HPC is what makes this operational because it allows us to run pre-processing, training, and inference quickly enough to retrain and generate outputs within decision windows. Practically, this translates the main bottlenecks into concrete outcomes, meaning shorter decision cycles through faster rankings, better generalization beyond single sites, lower cost and reduced risk by limiting trial burden, improved multi-stress assessment for resilience traits, and a workflow that can scale across regions and breeding programs. So the point is not only better modeling, it is making genomic selection deployable and repeatable in day-to-day breeding operations. In this slide, we summarize the shift that traditional breeding is slow, field trial intensive, and strongly dependent on current local conditions. Then Genesis adds a digital layer. It combines genomic data with environmental information and AI models, and then it uses HPC to process everything faster. So instead of waiting for many cycles before narrowing down candidates, breeders can receive earlier predictions and rankings. This supports faster decision-making, better climate awareness, and a more scalable breeding process. So let's talk of what Genesis does. Genesis is an end-to-end genomic selection pipeline that turns raw breeding and genomic and environmental inputs into actionable predictions for selection. First, it starts by integrating multi-source data. We specifically used ensemble plans, BIOS trials, datasets, and supporting weather, soil, and metadata into a single analysis-ready dataset. On top of that, we applied genomic and environmental aware feature engineering and modeling, so performance is predicted across environments rather than being tied to one site. And all the models were trained were trained using data from 6 different EU countries with different climate in different climate zones. And then this workflow was validated on real breeding data, and the outputs are delivered in decision form, genotype level summaries for ranking and sortlisting, and scenario evaluation where needed. Finally, execution on Meluxina HPC provides the computational capacity to accelerate pre-processing and training, so retraining can be performed frequently enough to align with breeding timelines. This is the architecture at high level. As we can see in the input layer, we have genomic data, phenotypic observations, environmental variables, etc. These pass through pre-processing and quality control steps where the data are cleaned, harmonized, and transformed into model-ready features. Then we have the modeling layer where different machine learning approaches are trained and validated. And after that, the inference layer produces predictions for candidate genotypes. Finally, the results are translated into outputs that are useful for breeders, rankings, shortlists, performance summaries, and reports. The important point here is that the architecture is designed as a repeatable pipeline and not as one-off analysis. So the main achievements from prototype benchmarking to HPC train selection is that MLP method gave the best stable baseline for width yield around with an R squared around to 0.64 and held out testing. All the tree-based methods underperformed here, suggesting that they didn't capture the complex interactions as well as this setup. The main value here was the main value of this stage was giving us a reproducible baseline and providing the pipeline end-to-end before scaling up on HPC. After that, we moved to HPC training and stronger validation. The outcome here is clear now, and that yes, MLP is the top model with the best accuracy and the lowest variance in K-fold validation. Even when a testing was held out, we confirmed that the ranking from the top for the top best methods were MLP first, then light GBM, and then random forest. And BIOS real-world validation improved the R squared for about 15 to 20% compared to the first baseline. Also, the model was trained again across the 6 countries we mentioned before, so it supports broader inference. The result is that MLP is our core method. And in this slide, we can see that the HPC reduces the total pipeline runtime significantly. So retrained and evaluation can happen inside breeding decision windows in hours and not days, as it was supposed to run if we didn't use an HPC. So that means that we can produce decision-ready rankings faster and run scalable scenario evaluations without delaying breeding operations. After establishing how Genesis works end-to-end, the focus shifts to what this enables in practice. For BIOS and other seed producers, the main benefit is faster selection and shorter breeding cycles, supporting earlier uptake of climate-resilient varieties. For research users, the workflow provides scalable genomic selection capabilities without requiring heavy local infrastructure. And for farmers and communities, they benefit through improved yield stability and better adaptation to climate stress. At a wider level, the expected contribution is towards food security and SME opportunities in digital breeding services and sustainability. On exploitation, Bespoke intends to further develop Genesis, while BIOS plans to continue using the platform to strengthen varietal evaluation and seed production services. Now, on the market side, plant breeding and seed technology is a large innovation-driven sector valued in the tens of millions of euros globally. In Europe, the landscape is broad. Around 5,000 seed companies operate across the EU, and the vast majority of them are SMEs, but it's also relatively concentrated, with a small group of large global breeders accounting for a major share of the market. Euroseeds is an important anchor in this ecosystem, with over 70 direct company members and representation across more than 30 national associations, which is relevant for outreach and uptake. A key point is the sector's high R&D intensity. Reinvestment can reach around 20% of turnover, reflecting strong capacity to adopt validated innovation. And within that context, Genesis is positioned in the digital printing segment. Our commercial focus in deliberately conservative targeting service-based uptake in 1 to 2% rate, which translates to an indicative 1.5 to 3 million in recurring revenue by years 3 to 4, subject to validation and adoption. So to summarize, the main lessons learned from using HPC was that the first lesson is data management. Genomic matrices and trial datasets are large, so efficient formats, compression, and careful I/O management are essential. The second lesson is reproducibility. On HPC systems, software dependencies and versions must be controlled carefully, so we use pinned environments and workflow automation. The third lesson is parallelization. Meaning scaling the workflow is not just about using more resources. We have to profile the pipeline and identify where job areas, vectorization, and parallel execution actually improved performance. And the fourth lesson is operational adoption. For HPC to be useful beyond development, the workflow must be understandable, documented, and repeatable. The main takeaway is that HPC creates the strongest value when technical acceleration is translated to a simpler decision workflow for the end user. Thank you very much. And if you have any questions.
Thank you, Melina, for this presentation. We have time for questions. What about the accuracy of the results when using the AI models compared to classical methods?
The accuracy depends on, first of all, it depends on the training. And if you have to spend more hours for training in the classical methods, you minimize the variables you use for the insight. So if your PC, let's say, doesn't let you to do many tries and have the best results, you have to, yes, you understand. So yeah, HPC, it's very crucial for that, for parameterization of the final model. And for using more complex methods. For example, there are many AI methods that can be run from a simple user PC.
Okay. And perhaps a second question concerning impact. How HPC improved your market vision or your customer search? Does this facilitate things for you?
I will give room to that to Gregory because it's his domain, if he can answer.
Melina, your screen. Let me clarify that having the opportunity to pilot test and validate such applications with industrial sectors is of utmost importance. Consider that no matter the hype with regards to AI, HPC, and so forth, when we move from the actual development to the operation and to the market stage, everyone traditionally requires, let's say, tangible, results that quantify their utmost importance, how important it is, how meaningful it is, and so forth. We had the pleasure to have BIOS in it, so for us not only to work alongside with an industrial actor that does this traditionally and has access to a number of markets, but also they were very close within all this progress of developing and validating, again and again, providing the data, providing operation data, and so forth. So this gives, let's call it, a stamp of accreditation by a potential end user at the end of the day of this application that is, of course, will be customized to their demands and requirements.
Yes.
Also for any future commercial customer, for us, it will be a certification that we did this So once you have the baseline data, we can quickly deploy it again for you. And as I said, like in any market, and like no matter, let's say, how hype marketing or pushing could be to the end users, having the ability to develop and demonstrate those, as this opportunity was provided to us by FFplus, is an exceptional first leg into rolling it into the market.
Okay. Thank you very much.
You're very
Gregory.
welcome.
Are there any other questions? If not, we can move to the second present. Thank you very much, Melina. Thank you, Gregory. Thank you.
Thank you very much, Samir,
It was nice to
for having us.
We can move to the second presentation, dealing with accelerating predictive maintenance workflows with HPC, made by George Stavroulakis from Nessos. George is a software architect and engineer, head of R&D department of Nessos Information Technology, which is a leading ISV company in Greece, focusing on niche technological projects in the field of business applications for the private and public sector. He has more than 20 years of experience in software development and system architecture, and is also an experienced in matter of civil and mechanical engineering. Please, George.
Thank you so much for the introduction.
Thank you.
So our project has to do with what is being called predictive maintenance, and it has to do with mechanical equipment and how we can optimize them with respect to their performance and their life expectancy, let's say. So before I begin showing you what we have done during this project, I will be saying a few words about the company. The company is called Nessos. Nessos is more than 20 years present in the Greek and international ISV sector. It's an SME. Its main job is to make software, and this software usually is bespoke and is tailor-made for the specific niche, let's say, needs of various clients, which are part of the public and the private sector, as Samir mentioned before. So apart from that, Nessos is also active in business and tech consulting and in team leading. And throughout the years, it has participated in various projects in quite lots of, let's say, areas with clients that are big companies in Greece and abroad as well. So besides the research and development things and actions, there is also some focus on financial systems, production management systems, and automations. And Nessos has been collaborating with the shipping sector and has partnered throughout the years with various shipping companies. Hence the need for this project, which has to do with mechanical equipment, as I will show you later on. So as I was saying in my introduction, the challenge that this platform solves, and has done so with the help of HPC infrastructure, has to do with the overall optimization, monitoring, and maintenance of industrial and in general mechanical equipment. So the whole notion here is somehow to, let's say, predict when a specific equipment is about to fail. And this also happens before the equipment fails completely, but starts malfunctioning, or it starts functioning in, let's say, a lesser performance, less performance state. So what we want to do here is somehow predict that and alert the engineering team about what's happening, so that it can infer where is the damage and what it can do in order to, let's say, salvage this equipment and extend the lifespan of the equipment involved. So the target, as I have more or less said before, has to do with the shipping industry. So the focus is what is being called shipping 4.0. Shipping 4.0 is actually the application of various technologies which are more or less mature and robust right now, which have to do with AI, IoT, and automation in general. And our target, since we are a Greek company, is on the Greek shipping industry, which is quite large, let's say. And as you can see, it's ascending in terms of monetary value. So why do we want to target this? Because all of the life cycle of equipment management and the maintenance per se comprises quite a big percentage, let's say, of the operational expenses cost of a vessel profit and loss. So if maintenance is poor, this means that the vessels have downtime, which of course, as you may know, it's of very big significance with respect to money issues, and it has a severe impact on profit. And of course, there is also the aspect of environmental and regulations, because poorly maintained systems can be really harmful to the environment, and of course to they might also be security, let's say, and the safety risk. So what are the current practices? The current practices are what we call reactive maintenance or run to failure maintenance, which means that we let the machinery more or less operate on its own, and when it fails, you just replace it. But of course, this has a very big impact of downtime, and of course, there is an optimization with respect to its lifespan. Moreover, there is preventive maintenance or time-based maintenance, which is also part of the regulations. And of course, there is also specific scheduled maintenance with equipment that is regulated by the IMO under the ISM code. These are maritime codes that have to do with safety. So what is the challenge? In order to do something like that and in essence have a digital twin of the machinery and see how this equipment operates and what state it's at, we have to process large data streams. So with the IoT, we have sensor input, which can be real time or can be aggregated. And all of this data have to somehow be, transformed into knowledge, so that the engineering team can really assess and make informed decisions with respect to the maintenance of the equipment at hand. Moreover, what we have introduced here, and I would say that this is the main thing that the HPC infrastructure has, let's say, shown its benefits and has enabled the project, as you will see later on, has to do with physics simulation. So what we want to do is gather these large streams of data and somehow understand how the equipment works and what are the parameters of the models that simulate this equipment, in order to get an understanding of the condition of the various modules that this equipment is comprised of. So in order to do that, as we'll show later on, we have to do simulations and then train some AI models to cut, let's say, the computational costs. I will talk about this in the next slides. So there are physics simulations involved, and this is quite an issue. Moreover, this issue gets really cumbersome because we have to account for various scenarios, and this means that the conditions of the machinery simulated might be different depending on how well maintained the machinery is, which means that we have to make more model runs, which have more computational cost, and of course this needs more computational resources, hence the HPC. And of course there is also a thing about uncertainties. uncertainties can infiltrate various aspects of what we are doing here, from how accurate the IoT sensors are to how perfect, let's say, the various modules of the machinery are. So in order to account for this, we have to again make more computations, more calculations, hence the need for the HPC. So this was the real challenge, and this is why having HPC resources in our hands and HPC, let's say, know-how was very crucial to the outcome of this platform that we have made in Nessus. So, as I was saying before, what we want to do is monitor the machinery and start, let's say, to see how any possible degradation of its performance starts and how it behaves, predict from that degradation a potential failure point, and considering this information, make an informed decision as to what to do with the specific machinery. So, as you can understand, this has to do with how crucial this machinery is to the operation of the whole ship. What's the cost for repair, if repair is possible when, for instance, the ship is at the sea. And all of these, let's say, conditions and all of this data are accounted for by the engineering team in order to make an informed decision. So what we do here is get sensory input from the IoT, from all of the sensors that are at the machinery, get the performance, compare this with the optimal performance, and from that make an inference as to what kind of failure or what kind of damage might have been done in the machinery that we inspected and we have a digital twin at. So in this project, we had, let's say, the opportunity to dive into three kinds of equipment. The first one has to do with the ship engine. So it's the actual engine of the ship with cylinders and its various equipment with the turbocharger and all of these things, as to how it operates. And from its operation and from its data, infer if there is something wrong and what could that be and what actions should we take there. There was also an inspection and a modeling of what is being called the ballast water treatment machines. So ballast water treatment is a process where when a ship gets water in its ballast in order to have specific floating, let's say, properties when it goes to the sea, it gets water from one port and then it removes it, let's say, gets rid of it in another port. And because there is biomass being transferred, there is regulation about purifying this water. So this ballast water treatment does that with various, let's say, ways. One of which is actually boiling the water. So this was quite a simple machine, but with quite intricate modes of failure that we have perceived there and we have monitored. That's the second machinery. And the third machine had to do with what we call the electrical generators. So in the ship, there is a need for electrical power, and for that there are electrical generators there. This again have some specific modes of failure, and we have made simulators for that as well. So what was the process? And here is where HPC, let's say, was involved. The process was first to make models of the machinery at hand. So we collaborated for that with an academic laboratory in the National Technical University of Athens, which is called the Group, and it has the know-how for HPC and also has an open source code that makes finite element model simulations. And it's quite, abstract and modular, so that someone can introduce various models for such simulation. So the first thing was to make these simulators and these codes. Then after developing those, there was a need for optimizing them in large, let's say, scale of granularity in an HPC environment with lots of nodes, that is. Then make lots of parametric studies. So for the various conditions I was referring to in my previous slides, along with the various models and the fact that these phenomena that we, let's say, examine are time dependent. So lots of time slots there, which means lots of calculations. And we gather all of these information from the simulations in order to calibrate our model, and from that calibration understand what might go wrong in some machinery. And from all of this data, train AI models. These are what we call surrogate models, which we, as I say, train with all of this data in order for these models to make predictions about new data from the machinery without the need of running these very accurate but also very expensive physics simulators. So we gathered data, we made lots of simulations, we generated even more data, and all of this data were fed as training material to surrogate models, which were then used for quick inference of the digital twins of the machinery that I have spoken in my previous slides. So the computations, so there was a need for very many computations, and in order to get a grasp of that, if we had like a very good 24-core i9 PC, in order to do the computations that we needed, we would need 4,000 days, which means that for 10 years we should have one computer and doing all of this number crunching. And as you can understand, such a magnitude of time makes such an endeavor completely infeasible. However, HPC came to the rescue. In particular, we utilized Aris infrastructure. Aris is a Greek HPC facility, national facility for HPC. And in total, we just consumed something like 3 months of computations. So this made actually such an endeavor feasible for us. And moreover, it also had, let's say, a side effect, which was for us to explore also public commercial infrastructure, cloud infrastructure, which can be comprised of many PCs, like in an HPC environment, in which we can also run our calculations and our models. And why this was very important for us, because shipping companies can be very, let's say, stringent with respect to the actual infrastructure that their code is executed on. So they might be very reluctant to utilize public HPC infrastructure. So we had the opportunity, let's say, to make this thing portable, not only to HPC infrastructure, but to cloud, general cloud infrastructure as well. So here is a real-world example where there are some graphs that, let's say, showcase how an engine might work, and it relates the power versus the engine RPM along with the turbocharger RPM, the efficiency in the turbocharger, let's say, horsepower that provides to the engine on top of that. And more or less what these slides want to say is that we get some data where there is a specific power output, specific engine input RPMs, and specific turbocharger RPM, and getting data from our simulation, we can infer that there is a problem with the turbocharger, and then we can instruct the team to check it out with respect to clogging, or maybe the impeller having some sort of problem, or poor lubrication and stuff like that. So this is a very brief example of what such a platform can do. The impact we consider is quite big. As I was saying before, having machinery operate in, let's say, their optimal rates and getting feedback about, their performance is really crucial, especially for energy efficiency, which of course also has to do with costs, and this is very important. Environmental issues, of course, are very impacted because an optimal operation means less energy consumption, again, is environmentally very friendly. And of course, there is the business aspect as well, which has to do with the general competitiveness thing, because utilizing less energy means less costs, which means that smaller companies can be more competitive, have more profit, maybe lower their price and stuff like that. And this whole platform, has been, let's say, is available, not has been, is available as software as a service. And as such, being, HPC friendly and, scalable, can be deployed across different EU regions, different computing environments, different HPC infrastructure, and so forth. So this is quite scalable and very, easy, let's say, to utilize from companies outside of Greece. So the current state that the software is, we are in a pilot operation with two big shipping or shipping-related companies. The one is now shipping, and the other one is Ocean King. They're quite big in what they are doing. And future developments have to do with introducing more machinery, not just the three ones that I've mentioned before, to make these kind of surrogate models and see how these can, function and operate on vessel and make, and optimize the state of the machinery. So this is pretty much it. You can visit www.maintain.gr to see what this thing is all about. And thank you so much. If you have any questions, or I would be really happy to answer them. Thank you.
Thank you. Thank you very much for the nice presentation. Any question? Do you target other sectors or other applications?
Sorry, can you repeat?
Do you target other applications than shipping maintenance?
So you are asking if we target with this simulator some other applications besides, you mean the machinery, the industrial equipment? That's your question?
Exactly. Yes. Yes.
Yeah.
Exactly.
Yes. Well, we don't have a business case per se right now in the sense that we have some demand, but we are collaborating with M Group in order to make simulators for medical applications as well. So
Okay.
there are things like, let's say, drug delivery, where you can make models of the vascular network inside, let's say, an organism or near, let's say, a cancer tumor, and optimize and see how drugs could be delivered. So despite such a thing being so different from mechanical equipment, the same equations apply, the same tools apply as well. We have the collaboration, we have the know-how, so there is some discussion as to how we can lay this down in a business sense. So yeah, we have quite some ambitious plans. Let's see how this will go.
Okay. Any other question? Can you chat or raise hand to ask questions? Perhaps another question. Surrogate models exist since several years, so since the years 2000, I think, if I remember. What is the added value of AI combined with surrogate models? What is the real added value?
Yeah. Well, the AI was used in two, let's say, positions in the pipeline. The first, which I didn't mention, has to do with the solution of the equations themselves. So M Group has some know-how with respect to accelerating iterative solvers, linear algebra solvers, by making preconditioners that are based on AI. So while we have finite element models, which have, the usual quite good accuracy, and linear algebra solvers that, again, you can focus on a very good accuracy, there are preconditioners AI-based which accelerate the solution. This was one thing. And the second thing was to train various AI models. Actually, it's machine learning, to be really, strict about it, so that such models can run in small computers, not small, I mean usual computers that someone can buy in the store, inside the vessel, so that there is no need with communication with, the shore, where there is this HPC infrastructure. So it's like having a less accurate but very fast prediction of things, so that if there is something that needs to be done quite fast inside the ship and there is no time for waiting with the shore, you can have some information from that part. So actually the main innovation has to do with having very specific to the equipment, fast AI models that can serve as digital twins in the ship. That's the main, let's say, focus and innovation, which, as it seems, is very useful to the engineering team. That's what we have understood from our collaboration with these two companies.
Okay, thank you, George, for this answer.
You're welcome. Thank you.
If no more questions, we can move to the third presentation, which is Foundation Model of Geospatial Analysis, made by Patrick Sabol. Patrick Sabol is a PhD, is a GeoAI and HPC specialist focused on building scalable geospatial intelligence. As lead R&D architect for the FFplus Innovation Study, he led the training of a custom vision transformer foundation model on the Mare Nostrum supercomputer. Leveraging his PhD and ESA project experience, he deploys his high-performance distributed AR architectures for real-world Earth observation. Please, Patrick.
Hello. Hello, everyone.
Hello.
Okay, can you see presentation?
Yes.
Great. Okay, so hello, everyone. My name is Patrick Sabol. I'm from Geodetica Vision, and let me present you our outcome from FFplus project called Foundation Model for Geospatial Analysis. In this project, our consortium consists of two partners, Geodetica Vision as SME and application lead, which defines business requirements and use cases, and our partner was Slovak Academy of Sciences, which role was HPC and AI technology partner. This Academy of Sciences provide us partially HPC infrastructure and is specialized in large-scale distributed AI training. In Geodetica Vision, we believe that world can be better placed when decision makers will make better decisions, and to make better decisions, it requires better understanding of reality, and without better information we cannot understand also reality, and we have to have better data for better information. Therefore, in Geodetica Vision. We are a Geo AI company based in Košice, Slovakia, and we handle the full pipeline from data collection using drones or aerial and satellites to processing of those data. And we use AI to extract information, basically turning pixels into classified layers like buildings and roads. And all those results we deliver through web GIS or digital twins for real world simulations. But our recent and last product is Cartographer platform, which is software as a service, which is designed to democratize high-end geospatial analysis. In this platform, you can convert raw satellite or aerial imagery into clean, usable map data, specifically vector polygons or lines in just a minute. And this platform allows non-technical users like city planners to perform complex mapping tasks without needing to be GIS experts. For Cartographer platform success, we are facing a critical business barrier, which is scalability, which we call the data hunger bottleneck. Basically, traditional AI models do not generalize well. For example, a model trained on Slovakia fails if we try to use it in other countries, which means that, for example, we have use case for which we labeled data for 6 months, where we spent more than 170 euros for labeling those data. And to move to another region, we should spend basically the same money and time. Therefore, the high cost and delay made global expansions for this platform economically impossible for us. The solution we present is to move from one model per task to new paradigm, which is to have one model for many tasks, which is basically some kind of foundation model, which means that instead of training from scratch every time for a new domain or data, we train one massive heavy generalist model once, and then we can rapidly adapt or fine-tune this model for new domain or data, which basically turns our AI into reusable assets, which slashes our time to market from months to just weeks. So in practice, the architecture look like this, that input to pipeline is any geospatial imagery across Europe, and foundation model will generate embeddings, which has deep context information from those imagery, and those embeddings could be used to train or fine-tune a model specialized in any kind of domain. And those models powers Cartographer platform to deliver segmentation or vectorization directly to the user. So the solution approach for this project was to first build or acquire massive data to train foundation model. Those data are not labeled, so it's much more easy to acquire. Then to train this model using vision transformer architecture, and finally a fine-tuned model on some of downstream tasks, which allowed us to validate this approach, whether we can train once and fine-tune everywhere. So to be specific with the steps, first we acquire large imagery from Europe. We aggregated around 17 web map services imagery from European countries, which are free available. And for these purposes, we implement some scripts to download those imagery. And for this purpose, we used HPC Devana, which is a small Slovak HPC machine. And we used around 100,000 CPU cores to massive parallel downloading and then processing of these data sets, which we where final data sets has around 6 million samples, and the size of the data set is 9 terabytes of data. HPC in this case help us a lot because when we use some dedicated local server with 20 CPUs for this task, the estimated time was 7 months to gather these data sets. But using HPC parallelization with all tests and so on, we completed this task in just 1 month. So the second step was to use those datasets and to train this foundation model, which is based on a vision transformer. And this model was trained using a self-supervised approach called masked autoencoder, which means that the input during training, the input to foundation model was masked imagery. As you can see, around 75% of imagery was masked. And the task for foundation model was easy, logically easy, to reconstruct this imagery to original, all those original pixels. This way, the foundation model is able to train all context and all embeddings from European geographic area. To train this model, the problem first was that raw European data is around 80% forest and vegetation, which create highly unbalanced data sets. For this purpose, we implement also custom balanced data loader, which means that for each training batch, we made sure that the data set was balanced, meaning we made sure that one batch consists of 3 urban imagery or 3 forest imagery and so on. We also use some optimization strategy to optimize hyperparameters for training of the large model, because we also train 3 smaller models to be used in any kind of use cases. And using tiny and small models, we found the best hyperparameters for training, and then apply this training for large model. Here, HPC, we used around 70,000 GPU hours using Mare Nostrum GPU or HPC in Spain. And we were able to scale or to speed up more than 48 times on 64 GPUs. And this helped us to compress the training time from 8 years on one single GPU into 1.5 months. Okay, so then we fine-tune some model using this foundation model. To be specific, we use our proprietary segmentation data sets of 14 land use classes. And first, we train exclusively on label data from Slovakia, and then validated the results on data from 5 other European regions. The results on Slovakia domain was that foundation model comparing to training of the very same model, very same architecture, but from scratch, not from a pre-trained model. The improvement on this dataset was 18%. And what is more breakthrough for us is that we found out that when we train a model with only 12% of data, of original label data, we were able to train or fine-tune model which is almost the same performance as the model with 100% of data. So this breakthrough has strong economic advantage for us, because with this data reduction of 87%, we can also reduce the labeling cost for new data sets or for new region, which means also that we can spend much fewer time on labeling, which means we can deliver 6 times faster the new models to customers. And return of investments of this project was more than 140% when we realized this with just 2 more data sets, which means that we can directly deliver this product to more than 700 European municipalities. And this brings us a projected revenue of our cartographer platform for next 3 years with 2.6 million euros. And mainly this project, through this project, we were able to save more than 300 euros in cloud savings when comparing to GPU commercial providers. Well, what this project means for Europe in general, who benefits in Europe from this project? Primarily are the end users of cartographer platform, which are mainly municipalities and government agencies, to which we can bring new data, new model with less cost. Also, by providing or open source this model and data sets, European SME and startups and research and academic community could benefit from this project. As I said previously, by bringing down the time and the label and cost for new models, this way we can scale faster across European regions by not retraining from scratch every new models and bringing new models 6 times faster. From socioeconomic impacts, basically this project and our cartographer platform, we are democratizing AI by, as I said previously, bringing the lower cost for new models. But mainly we are strengthening European sovereignty by delivering European model directly for European people and region, because it was trained on European data. And also we enhance crisis response because this model could be fine-tuned faster on such cases or domains such as floods and wildfires. So what is next steps with this project or platform? We are about to launch the full commercial version of Cartographer platform, and we are directly aimed to European municipalities. And for the future, the logical step is to go from a purely or vision-only foundation model to move to vision language foundation model, which user could benefit in the way that model will understand semantic input from the user, and user will be able to this way using text directly generate not some segmentation maps, but directly polygons, vectors, lines ready to use for their geospatial analysis. So that's all from my side.
Do you see any other application for the methodology used for cartography here? I mean, other applications like pollution or something like that? Is it applied?
Yes. Yeah, basically, this is foundation model, which is able to understand imagery from Europe, and then it could be used in any kind of domain which has some labels. Like, I don't know, there are some application for pollution where the data is, I don't know, they have labeled some pollution area or something like that, and if they want to detect this pollution from imagery, they are able to use this foundation model to fine-tune.
Okay. Thank you, Patrick. If no questions, we can move to the last presentation.
Thank you.
Thank you, Patrick. So this, the last one, is dealing with from high fidelity simulation to real-time models. HPC-driven reduced order models for enhancing industrial thermal process efficiency. This will be made by Antonio Gomez from Nabladot. So Antonio is a founding partner and R&D manager at Nabladot. He holds an award-winning PhD in renewable energy from the University of Zaragoza. He has extensive expertise in computational fluid dynamics, energy systems modeling, and renewable energy. He has participated in over than 100 European national and industrial projects and has authored 26 peer-reviewed journal articles. His recent work has focused on adapting advanced simulation techniques for Industry 4.0 with a specialization in HPC digital twins and industrial process modeling across multiple high-profile European initiatives. Antonio, the floor is yours, please.
Okay, thank you for the presentation. Could you see well the screen, I think?
Yes.
So,
yes.
Okay, thank you. So, well, in this presentation, we summarize the results of the Ignite project, in which we develop our reduced order model using HPC resources in order to optimize and improve the performance of industrial fire preheaters. I am an R&D manager of Nabladot. Nabladot is an SME that we are experts in computational fluid dynamics, providing simulation services to other industries. And in the last years, we are working a lot in developing this reduced order model and industrial digital twins. In this project, we work with Calfrisa, that it is manufacturing company that produce heat transfer equipment, heat exchangers, and other equipments for the thermal processes at industrial level, and also with the University of Zaragoza that they provided expertise regarding HPC resources and data analysis. The challenge that we face when we are dealing with heat exchangers and industrial equipment related to heat transfer is that they are relatively complex equipment. They combine different fluids, gas side, air sides, combustion, radiation, convection, conduction, complex phenomena in order to be simulated. And additionally, the geometry of these equipments are very complex. You have thousands of pipes. There are burners. Sometimes inside the pipes you have turbulators. Using traditional techniques like computational fluid dynamics, of course, provide value, but it's complicated. It's complicated, but in many cases you require tens of millions of cells in order to represent these geometries in a way that the simulation can provide accurate results. Therefore, many of these companies don't use computational fluid dynamic techniques and still rely on semi-empirical models, correlations, and their expertise and experience. But this has limitations. For example, these methods cannot capture some of the phenomena that are occurring in the heat exchangers, and also increase the uncertainty about the design. Sometimes, or many times, this equipment is over-dimensioned in order to avoid problems, in order to don't meet the performance that is required. And also, these methods cannot be incorporated or integrated in digital twins or predictive maintenance tools. So the innovation that we tested and demonstrated in this project was to create a reduced order model that is able to capture or to have the accuracy or similar accuracy of high fidelity simulations, but reducing considerably the computational time. The key features of this, the envisioned reduced order model, is that it can be executed in real time. The accuracy is similar to CFD models, maybe deviation below 10, 50% at a maximum. And the room can be designed for or tailored for the client's requirements. This is really important because sometimes in order to use CFD, manufacturers companies need to have some expertise in CFD. But with these reduced order models, they don't need expertise in CFD, and you can design intuitive interfaces. And also, as I have mentioned previously, these reduced order models can be integrated into engineering workflows of the companies and also in digital twin platforms. This is our case study. As you can see, is a fire preheater, which consists of a burner. In general, they use natural gas as fuel, and also there are in the periphery of this burner, there are around 200 tubes with dimensions probably more than 8 meters and 10 or even more, but I think that the minimum size is 8 meters of length. These tubes can have or not turbulators inside them in order to improve the air heat transfer. And the modeling of this equipment with CFD is also complicated. It's complicated because, well, you have to simulate the combustion, the airflow inside the tubes, the geometry. There are you have a strong multi-scale character in this equipment. So probably you would require about 30-40 million cells in order to use CFD to simulate this equipment. Even that, it would be very just in order to obtain accurate results. And in order to design this, sometimes it's too slow in order to wait for the results of computational fluid dynamics simulation. So reduced order models are within our or can be or can have a good potential in order to be introduced in this type of equipment, in this type of companies that manufacture heat exchangers and related equipment. What do we do in order to create this real-time model, this reduced order model? In the first place, we characterize the performance of the tubes. To do that, we run multiple simulations of the outer side of the tubes in order to obtain this fluid gas state coefficient. We run around 260 CFD cases using a computational mesh around 8 million cells. And then we extract the results and we obtain a correlation for obtaining the fluid gas heat transfer coefficient using symbolic regression techniques. And we did the same for the inner side of the tubes, the outside coefficient. In this case, these tubes can have different lengths and also turbulators, different geometries of the turbulators. So we run around 240 CFD cases with 6 million cells. And also we obtain a correlation for the heat transfer inside the tubes. With all these simulations, we cover all the possible options regarding the tubes that you can have in order to design this equipment. And in the next step, we created a very simplified simulation with CFD using around 8,000 cells. This can run in 5 minutes. With this is a two-dimensional simulation that it is able to provide us the radiant heat exchange and the flame behavior and the flue gas temperatures close to the tubes. With this data, we fit the heat transfer correlation that we have obtained previously, and we are able to obtain the heat transfer in these tubes. In the next slide, you can see the results that we are able to obtain. So we can obtain with this reduced order model that is executed in 5 minutes. The flue gas temperature and other graphs, flue gas velocity or something like that, and also reports showing the the energy balance, calculating some KPIs. So all the information that it is required by the manufacturer. And also we validated the results with real data, and certainly the validation was very satisfactory in order to obtain the temperatures of the flue gas at the outlet, and also the temperature of the air at the outlet of this equipment. Why the HPC has been essential for the development of this reduced order model? At the end, we have generated synthetic data with HPC, and we need around 500 CFD simulations, and with computational methods around 6-8 million cells. We use 280 HPC cores, and we obtained the full data set in approximately 1 month. If we would have used a 8-core workstation, a typical workstation for calculations, obtaining the data set would have required around 11 months, which it is unfeasible in order to develop this mode. So certainly this HPC resources are really very useful for that. Also, something relevant and important in order to get that these models are feasible, economic feasible, is that we have run the simulations with open source software. If you have to pay license for this number of HPC cores, probably it wouldn't be feasible to produce this reduced order model. What is the impact on the engineering workflow? For example, if our manufacturer company, Calfrisa, would decide to use CFD for designing their 5 preheaters, we estimate computational methods around 30 million cells, and more or less 7 days in order to obtain a solution using, well, a considerable number of cores, of HPC cores. So probably we estimate around 5-10 CFD cases in order to analyze the influence of variables like tube length, the fuel, burner configurations, the turbulator types in the tubes. So at the end, you need around 5-10 weeks in order to be close of the final design. And if you don't have CFD capabilities in order to do this, and Calfrisa contracted a specialized CFD company, probably the study cost would be around 30,000-50,000 euros. If a reduced order model is used, the design of the equipment can be, the design time required for the equipment would be around 1-2 days. Certainly, if you have to generate this reduced order model, well, it takes some time, effort, engineering effort, but you can amortize the cost of the reduced order model, probably with the design of two 5 heater equipment. So, and additionally, you can use this reduced order model in order to implement it in digital twins or other platforms. So it can be quickly amortize the generation of these reduced order models. And since currently Calfrisa is not using complex methods for the design of the industrial preheaters, Calfrisa estimated that the efficiency of their equipment can be increased up to 30%. Also, they acquired the capability to evaluate replacing the natural gas, but for example, renewable gases like hydrogen, to offer a new digital twin services for their clients, and the estimated economic savings thanks to these new methods are around 120,000 euro per equipment and year, and also there is a considerable reduction of CO2 emissions. In this project, at the end, we have developed not only a reduced order model for a specific equipment, also we have tested a methodology that can be applied to multiple thermal processes. And certainly, the potential of these methodologies for this sector, we think that it's relevant. Around 74% of the energy consumption in the industry is dedicated to thermal processes: heating, drying, evaporation, distillation, calcination, combustion. So the potential to save fuel consumption and energy and CO2 emissions within this is very high. And it is reported in the scientific literature that digital twins and also real-time reduced order models, because at the end, a digital twin needs models based on data or based on physics. It's the same, but you need a model that provides you answers and recommendations. So it is reported in the scientific literature that with digital twins, you can reduce the thermal energy consumption about 10%, 35%, depending on the process, reduce the maintenance costs, CO2 emissions, and also the unplanned downtime considerably. So we think that this approach of models, of real-time models, can have a strong impact in the industry. And regarding conclusions and next steps, we think that we have demonstrated the potential of rooms and the need of the reduced order models and the needs of HPC resources in order to generate these real-time models. An important thing is that these reduced order models are built on open source components, so this facilitates the scalability. Calfrisa is going to incorporate the tool we have developed into its engineering portfolio and workflow. Also, we explore together with Calfrisa the adoption of this model in digital twin solutions. In October, we will start a project funded by the Judeca's Eurostar program. This project is called iTwinTs, Intelligent Platform for Rapid Deployment of Scalable Digital Twins in Thermal Industry Systems. And one of the objectives of this project is to create a standardized run generation process in order to accelerate the process of generating reduced order models and applying this for different families of thermal equipment, because at the end there are multiple heat exchangers or thermal processes. So the idea is to have a wide library with methods in order to to build these reduced order models. And additional, well, we would like to collaborate with industrial partners, tested in digital twins for thermal equipment or equipment manufacturers. And that's all. Well, this is so. Thank you.
Thank you, Antonio.
Mm-hmm.
This is interesting.
Mm-hmm.
Any question from the attendees? Do you think it can be easy to use the reduced order models in optimization workflows or in uncertainty quantification? Do you plan to do that?
Yes. Our idea is to still working on this in order to improve the methodologies, to accelerate the methodologies in order to create these models. And also we want to promote the use of this model in the industry, because I think that they can improve the current standards and the current software that they are using. And the last part is working on digital twins and with other companies in order to incorporate these models in digital twins. Yep.
Thank you, Antonio.
Mm-hmm.
Any other question? If not, I will conclude by thanking the participants for these nice presentations, these success stories from diverse applications and sectors, which all use HPC to set up the methodologies and the models for their sectors. Thank you very much. The last session of the webinar is on next Friday at the same time at 2 p.m. We have 4 more presentations and success stories to be presented next Friday. So hope see you next Friday. Thank you very much.
Thank you.